Hi, I introduced you a general nonlinear regression model. This is a very general nonlinear regression function, and we had to think about how we measure the effect of a variable on the outcome. So I told you the idea is we need to fix the other variables constant and then change only one regressor, say x1. So and you can define the effect on y in this way. So the other variables are fixed, and this is the ceteris paribus effect on y of x1. So it's same thing. And you may consider, you may understand this as a kind of differentiation, the derivative. So think about the derivative of a linear equation. So if you had this linear equation, y equals the outcome equals to beta 0 intercept plus beta 1 x1, beta 2 x2, and there are k regressors and add a term. In this case, the derivative with respect to, say, x1 is the variable of your interest. So the derivative with respect to x1 is simply beta 1. So the other variables are not, they are fixed and they have no effect on x1. So beta 1 is just a constant effect on y of x1 no matter what the other value is and no matter what x1 takes. So this was a very nice result. It simplifies a lot of things. So you just need one number to capture the effect of x1 on y. However, if you think about different functions, still simple, say, for example, think about a quadratic function. You have only one regressor, say x and x squared, and then in this case y is a function of beta 0, beta 1x, beta 2x squared plus error. In this case, if you take the derivative with respect to this regressor, you have to differentiate this and this. So the quadratic term, the second order term, its derivative becomes 2 times beta 2 times x. So as a whole, the effect of x on y equals beta 1, which is the linear term, plus 2 beta 2x. What is special here is that the effect, the derivative, it depends on x itself. So the effect of x on y can vary depending on where your x is. So exactly this is the income example. Depending on what is your income, the effect of the stimulus check on your life can be different, right? So same idea is coming here. So now it's not simple anymore. You have to specify what is beta 1, what is beta 2, and what is the value of x you have in mind. This is an example, just a simple an example from one of the simplest nonlinear equation. And another example here. Now think about here beta 0, beta 1, beta 2, so far the same, but beta 3 is a multiplication of x1 and x2. So x1 and x2 are multiplied. In this case, again, the derivative with respect to x1 has to differentiate this guy. x1 appears here, and another x1 should be differentiated. So you have to differentiate beta 3 term. So as a result, you get beta 1 plus beta 3x2. So beta 1 from here, beta 3x2 from here. It means that from this derivative, you can see that the effect of x1 on y the effect of x1 on y depends on x2, right? So now you have to specify, to study what is the effect of x1 on y, you have to specify x2. When you combine these two guys, so think about quadratic term is included in here, then everything comes into effect when you consider the effect of x1 on y. So this is this illustrates how powerful the linear assumption was. The linear equation assumption was a very useful, very powerful assumption, but as you see before, it's not true anymore. And relaxing the linearity assumption is not much difficult. Let's see what happens. We are going to consider two most common and simple approaches to nonlinear functions, nonlinear relationship. The first is the polynomials, considering the polynomial equation in X, say quadratic or cubic or higher degree polynomial, which is pretty simple. And the second approach is to consider logarithmic transformations. This is very interesting. Later we are going to discuss it in more detail. And this approach, log transformation, is maybe the most common way to handle the nonlinearity. So today, let me explain a little bit of the polynomials approach. So this is the polynomial. So simply consider one regressor, x, and include more than linear. So if you include beta 0, beta 1x, that is linear function, but you include squared and cubic squared, and like you can include more. It's up to you how many terms you include, but usually it does not go more than fourth. Usually linear or quadratic is enough, but if you want to be a little more rigorous, I have seen some work considering up to fourth order polynomial, but more than fourth order is not that effective. I mean, so does not have much big difference in the result usually. So, and it is quite similar to the multiple regressor case, say x1, x2, xr. Yes, it is. Yeah. Of course, x2 is now x squared, and xr is now x to the exponent of r. But it's no problem because you can calculate if you have data on x, like say think about Excel spreadsheet. So in a spreadsheet you have x, and then you can define x squared on the next column and x to the exponent of 3 on the next. And so more higher order polynomials can be defined as if it is a new variable. So then in the end, the polynomial regression is no different from multiple regressor regression. So all the methods like estimation, OLS, hypothesis testing, confidence interval, like say F statistic or like confidence set, everything is equivalent to multiple regressor case. However, of course, the difference is the coefficients interpretation. Interpretation is a little bit different because they are linked together, x and x squared. So when you change x, you cannot fix x squared constant. So when you increase x, automatically everything will change. So in your interpretation, you need to take that into account. Here is an example. Say as before, like this is the example we considered before. Income is the cause of nonlinearity, and test score is the outcome. So you may include income squared, and additionally you may include income cubic squared. Uh, if you want, you may go on and on, but let's just, I think squared will be enough, maybe. Let's see how it works. So then let's see what happens if you include quadratic term only. So this is your regression, your Stata code. Remember, we used generate. Generate command, we use generate command in homework 4. So this defines a new random variable. Generate a new variable, average income 2, which is defined as average income times average income. Then this is quadratic term. And then regress test score on average income and average income 2, which is the squared term. And then it is like another variable. So you may use these numbers as much as you want, like in the same way as you did for the multiple regression. However, and the fitting. Okay, let's think about the scatter plot. So by including the quadratic term, now your curve can be curved. Your line, trend line can be curved. So it looks like this. This is the best fitting line, quadratic function line. And linear regression, compared with the linear regression, quadratic regression must be better because you are including additional variable. Remember, including additional variable always increases the R squared, the explanation power. So in terms of the R squared, quadratic regression will do better. By the way, and let's have a look at this. The t statistic is -8, which is very large in magnitude. So, and the p-value is 0. So the quadratic term is very significant. That means you had to include quadratic term is important, and like doing something, playing an important role, like significant role in explaining the outcome. Yes, as you can see from the picture. So there is a significant difference between regression fitting and quadratic fitting. So quadratic function, a quadratic term is significant because of the big difference. And the problem here is how can we compute the slope, the effect of income on test scores? As I said before, as I explained using differentiation analogy, you have to specify x. Like think about this quadratic function. When you differentiate a quadratic function, the derivative is another function of x. So you have to tell what is the value of x, right? So in this example, I specified. Let's think about these two numbers. Specifically, change, we'll consider a change from 5,000 to 6,000. And then you can calculate. So then what you need to do here is you can predict the test score at 5,000 and predict test score at 6,000 and take their difference. That is done here, right? So this is, the first line is the predicted test score at 5,000, and in the parentheses is the predicted test score at 6,000. Excuse me. So outside parentheses, the first line, the above line is the predicted test score at 6,000. So 6 means $6,000 and $6,000 squared. So income was measured in $1,000. And in the parentheses is the predicted outcome at $5,000. 5. So their difference is 3.4, and note that it is different from the linear slope. the slope is linear, but the second order slope is negative number. So as a result, the slope should be 3.4. So, and if you think about different points, so we just considered change from 5,000 to 6,000, but if you consider 25,000 to 26,000 or 45 to 46, all of them are $1,000 difference, but their effect on test score is clearly different, very different. So as I explained earlier, if you already make a good income, then additional $1,000 is nothing. So there is no additional increase. And so the effect of additional $1,000 decreases. It's a diminishing marginal productivity, right? So exactly like it's a concave function in our example. And as an econ major, you should have a good intuition on the diminishing marginal productivity. So you may try this, but one thing important here is the problem here is it is a quadratic regression. So at some point, quadratic function is either looks like U or inverse U shape. So, but in this case, because the slope of the quadratic term is negative, this functional form, this function implies of a graph of like this, inverse U shape. So it's like what is it, like bell curve. So the quadratic regression function will go down at some point. So maybe maximum is achieved here. After this maximum, it starts to decrease. And maybe at this point, it will decrease like this. So the problem here is, there is no problem up to this point. However, if you try to predict what is the expected test score at, say, like $100,000, it will go, maybe it can be even lower than the poorest household. This is a problem because you are trying to predict outcome outside of observations. So you never observe $1,000, like $100,000 household, but you are predicting them using a quadratic function. Then by construction of the quadratic function, it will go in the other direction at some point. So you should be very careful, and you will see what happens if you calculate the effect of $1,000 between 65 to 66. It should be negative, which is not the model problem or the data problem. It is your problem. You should not interpret this way, or you should not extrapolate outside of the data range. Okay, I will do the lecture and see you on Wednesday. Bye.